Dear students, welcome back to the lecture series on solid state. In the previous classes, we have seen that crystals can be used as diffraction gratings for X-rays. We have also discussed about the Bragg's law based on the diffraction of X-rays by crystals. So today, let's discuss about the Bragg's X-ray spectrometer method. We have seen that crystals can act as natural three-dimensional diffraction gratings for X-rays because their atomic planes are spaced at distances comparable to X-ray wavelengths. We know that the wavelength of X-rays is generally of the order of 1 angstrom, and 1 angstrom is 10 to the power of minus 10 meters. So, the spacing between the atomic planes in the crystal is also of the same length. And when X-rays strike a crystal, they are diffracted or scattered by the atom, and this diffraction produces a characteristic pattern. And why crystals can be used as diffraction gratings for X-rays? As we said earlier, because of its regular periodic structure. We know that the crystalline solids have a regular repeating three-dimensional arrangement of atoms. So, this regular periodicity in atoms can create planes of atoms with consistent spacing. In addition, the distance between these atomic planes in a crystal is on the same order of magnitude as the wavelength of the X-rays. As we saw earlier, the wavelength of the X-rays is of the order of 1 angstrom. The spacing between the atomic planes in a crystal is also of the same magnitude. So, this match is very crucial for the interaction to produce characteristic diffraction patterns. And what happens when X-rays strikes on the crystal? They are diffracted or scattered by the atoms. And because of their ordered structure, these scattered X-rays interfere constructively in specific directions and destructively in others, creating the observed diffraction pattern. Interfere constructively means there will be a constructive interference. Constructive interference is a condition for maximum intensity of the diffracted beam or maximum intensity of the reflected beam. And constructive interference means all the waves will be in phase. And destructive interference means it will be out of phase. So, because of the ordered structure of atoms in a crystal, the scattered X-rays may either interfere constructively or destructively in several directions, and as a result they can produce the observed diffraction pattern. We have also seen that Sir William Henry Bragg and his son Sir William Lawrence Bragg developed a powerful method for studying the internal structure of crystals using monochromatic homogeneous X-rays. The father and the son were jointly awarded the Nobel Prize in Physics in 1915 for their contributions in the field of X-ray crystallography. And they also developed an equation or law known as the Bragg's equation or Bragg's law. We have already discussed about the Bragg's law or Bragg's equation. Let's rewind it once more. And what is Bragg's law? It states that when the X-ray is incident onto a crystal surface, its angle of incidence theta will reflect back with the same angle of scattering theta. Okay, so the angle of incidence is theta, the angle of scattering is also theta. And also for a strong reflection or diffraction to occur, The condition for a strong reflection or diffraction is that the path difference between the X-rays reflecting from the adjacent planes in a crystal must be an integer multiple of their wavelength. Okay. So, the condition for strong reflection or diffraction is that the path difference between the X-rays reflecting from the adjacent planes, and that must be equal to an integer multiple of the wavelength, and that results in a constructive interference. So, this is the Bragg's law, and mathematically it can be represented as n lambda equals 2d sin theta, where lambda is the wavelength of the X-ray, d is the spacing of the crystal layers, theta is the incident angle, that is the angle between the incident ray and the scattered plane, and n is an integer, and n equals 1, 2, 3 etc., which is also called the order of diffraction. If n equals 1, it is a first order diffraction, n equals 2, it is a second order diffraction, and so on. So, on the figure you can see that there are a lot of atoms arranged regularly in different planes. You can see the X-rays falling onto the atoms in the crystal and then getting diffracted. So, the angle of incidence is measured as theta. The spacing between the atoms in the plane is represented by d, which is called the interplanar spacing. Okay. So, n lambda equals 2d sin theta is the well known Bragg's equation or Bragg's law. Now, on the screen you can see the image of the original Bragg X-ray spectrometer developed by William Bragg at Leeds University. So, now let us see what is the Bragg's X-ray spectrometer method, or it is also known as the rotating crystal method. The rotating crystal method is an X-ray diffraction technique that uses a single large crystal mounted on a rotating spindle and illuminated by monochromatic X-ray beam. Okay. So, this method is called the rotating crystal method. It is an X-ray diffraction technique, and this rotating crystal method is originally known as the Bragg's X-ray spectrometer method, and this uses a single crystal which is mounted on a rotating spindle and illuminated by a monochromatic X-ray beam. Since a single crystal is used, this method is also known as single crystal method. So, the rotating crystal method or single crystal method. Now, as the crystal rotates, different sets of lattice planes periodically satisfy the Bragg's law, producing diffracted beams. The resulting diffraction pattern or the beam is recorded on a photographic plate or a cylindrical film, allowing for the determination of the crystal's interplanar spacings. We can also determine the unit cell dimensions and also atomic arrangement. Okay. So, now let us move on to the experimental part of the rotating crystal method. So, the figure on the screen shows the experimental setup of the rotating crystal method. We have an X-ray source that can generate a monochromatic beam of X-rays, and generally molybdenum K alpha radiations or copper K alpha radiations are used as X-ray source. And then we have a collimator or a slit that narrows and aligns the X-ray beam. Next is the crystal, a single crystal which is mounted on a rotating stage. And then we have a detector that can detect the diffracted X-rays. The detectors usually used are either an ionization chamber. An ionization chamber is the one which contains an easily ionizable gas. So, when the diffracted X-rays enter the ionization chamber, those X-rays can ionize the gas inside it, and those ionization can be recorded by an electrometer. Okay, so that is an ionization chamber. Or we can use a photographic plate which can directly capture the images of the X-ray, diffracted X-rays falling on it, or we can also use a Geiger counter. And this detector is mounted on an arm that rotates to measure the intensity of the reflected X-rays. There will also be a goniometer that ensures precise rotation of both crystal and detector. As you can see in this figure, we have an X-ray tube which generates X-rays usually from a molybdenum K alpha or copper K alpha. Then that is passed through a slit, and this monochromatic beam of X-rays is allowed to fall on the crystal. So, this is the crystal, and this crystal is mounted on a rotating disc. So, this is the rotating disc, and this disc is graduated to allow the precise measurement. So, this disc can be rotated, and what happens when X-rays fall on this crystal? It will get scattered or diffracted onto the detector. So, when it reaches the detector, it can be detected. Either it will be, the detector can be either an ionization chamber or a photographic plate or a Geiger counter. And the peculiarity of the detector is that the detector can also be rotated along with the crystal. So, as the crystal is rotated with varying angles of theta, the path of the detector can also be rotated. Now, let us see how it works. So, as we have seen, a narrow X-ray beam is generated in an X-ray tube, and that is passed through a slit to get a very narrow beam. And this X-ray beam is allowed to fall at a certain angle theta, which we may call the glancing angle or the incident angle theta, on a particular face of a large single crystal mounted on a graduated turntable. As you can see in this figure, the crystal is mounted on a graduated rotating disc or rotating table, and the X-rays, the monochromatic beam of X-rays, are allowed to fall on the crystal at a particular angle theta and onto a particular face of a large single crystal. Now, what happens when X-rays falls on the crystal? The diffracted rays are allowed to pass into an independently rotatable recording device. The diffracted rays will then move on to the detector, and here the detector we use is an ionization chamber. As we said earlier, it contains an easily ionizable gas like sulfur dioxide, and that is connected to an electrometer. Now, when X-rays enter the ionization chamber, it will ionize the gas inside the chamber, producing a current, and that current is measured by the electrometer. The greater the intensity of the diffracted beam, greater will be the ionization produced in the gas, and hence greater will be the electrometer reading. Okay. So, we have seen the working of the Bragg's X-ray spectrometer or the rotating crystal method. We have an X-ray tube which produces X-rays, and those X-rays are allowed to pass through a slit to get a narrow beam. The X-rays are allowed to fall on the crystal at an angle theta. The crystal is placed on a rotating disc which can be rotated. The diffracted rays from the crystal are allowed to fall onto the detector, and the detector used here is an ionization chamber which contains an easily ionizable gas like sulfur dioxide. So, when the X-rays enter the ionization chamber, what happens? These X-rays can ionize the gas inside it, and that produces a current which is measured by the electrometer. And the greater the intensity of the diffracted beam, the greater will be the ionization produced in the gas, and hence greater will be the electrometer reading. Now, when the crystal is slowly rotated about an axis perpendicular to the beam, let us see what all changes occur. At certain orientations, those crystal planes which satisfies the Bragg's condition, and what is the Bragg's condition? N lambda equals 2d sin theta. So, some crystal planes satisfy the Bragg's condition. So, when such crystal planes satisfy the Bragg's condition, there will be maximum reflection or there will be a strong reflection. So, such strong reflections are detected by the detector and it registers a peak, or it gets detected by the detector. Okay. So, when the crystal is slowly rotated about an axis perpendicular to the beam, at certain orientations, some crystal planes satisfy the Bragg's condition, that is n lambda equals 2d sin theta. And satisfying the Bragg's condition means there will be a constructive interference happening, and constructive interference means there will be maximum intensity of the reflected beam. The maximum intensity of the reflected beam will get detected by the detector. So, by measuring the angle theta, we can calculate the interplanar spacing d. Now, the experiment is repeated for multiple angles to generate a diffraction pattern. So, on the screen you can see a X-ray diffraction pattern captured on a photographic film. The spot at the center, the dark large spot at the center is a spot created by the X-ray beam, and surrounding the central spot you can see several small spots, dark spots here in a particular pattern, and those are the spots created by the diffracted X-rays. So, this is how a rotating crystal method works, which is also known as the single crystal method or the Bragg's X-ray spectrometer method. Now, we can see an animated video of the rotating crystal method. You can see the X-rays generating from the X-ray tube and falling on the crystal at an angle theta. You can see that the crystal is rotated on a rotating table, and by varying the angles, you can see that at some angles the planes satisfy the Bragg's condition n lambda equals 2d sin theta. So, you can see that the diffracted rays are detected by the detector. You can see that the detector is also rotating along with the crystal. Now, let us see what are the applications of the rotating crystal method. The main application of the rotating crystal method or the Bragg's X-ray spectrometer method, which employs the diffraction of X-rays by crystals, lies in determining the unknown crystal structures. Okay. So, determining the crystal structures of NaCl, diamond, metals, metal complexes, etc. It also allows for the measurement of interplanar spacing d. It also helps to identify unknown crystals, and this method paves the foundation for all modern X-ray diffraction techniques that we use today. Okay. So, these are the applications of the rotating crystal method. It helps in determining the crystal structures. It also helps to the measurement of interplanar spacing d. It also helps in identifying the unknown crystals and also used in X-ray diffraction analysis, all modern techniques that we use today. Now, let us see the crystal structure of NaCl, that is how we can interpret the crystal structure of NaCl from the X-ray diffraction data. It is given that the first order diffractions from the 100, 110 and 111 planes of cubic NaCl for X-rays from a palladium anticathode are observed at glancing angles of 5.9 degree, 8.4 degree and 5.2 degree respectively. Okay. Now, what is Bragg's law? Bragg's law, we know that it is mathematically it can be represented as n lambda equals 2d sin theta. So, from this you can calculate the interplanar spacing, that is d, the spacing between the atomic planes, d equals n lambda by 2 sin theta. It is given that it is a first order diffraction. So, always the value of n is equal to 1. The wavelength of the X-rays lambda will also be constant in a particular experiment. So, if these parameters are constant, then we can write d proportional to 1 by sin theta. So, then we can calculate the interplanar distance ratio. We have 3 planes D100 is to D110 is to D111. So, this is the interplanar distance ratio. So, this will be equal to 1 by sine, for D100 it is 5.9 degree. So, sine 5.9 degree is to 1 by, for D110 it is 8.4 degree. So, 1 by sine 8.4 degree is to 1 by, for the 111 plane it is 5.2 degree. So, 1 by sine 5.2 degree. So, if we calculate the ratio, that is approximately equal to 1 is to 0.704 is to 1.136, and this ratio is very close to the ratio 1 is to 0.707 is to 1.154, which is the theoretically predicted ratio for a face centered cubic lattice. Okay. So, from the X-ray diffraction data, we can identify the cubic lattice to which sodium chloride belongs to. Okay. So, you are provided with 3 different planes and the 3 glancing angles. So, using Bragg's law, we have calculated the interplanar spacing d, and we have seen that if other parameters are constant, d is proportional to 1 by sin theta. So, from this we can calculate the interplanar distance ratio like this, and we get the ratio very much similar to the theoretically predicted ratio for a face centered cubic lattice. So, we can say that sodium chloride belongs to a face centered cubic lattice. Now, when we analyze the X-ray diffraction of NaCl, we can see that with increase in order n, reflections from 100 and 110 planes show a gradual decrease in intensity, whereas those from the 111 planes show an alternate rise and fall. Okay. So, with increase in the order of diffraction, increase in the order n means n is the order of diffraction. So, with increase in the order of diffraction, we can observe that reflections from the 100 and 110 planes show a gradual decrease in intensity, whereas those from the 111 planes show an alternate rise and fall. So, from this we can interpret that all 100 planes are equivalent. Similarly, all 110 planes are also equivalent. That means there are equal numbers of Na plus and Cl minus ions symmetrically arranged. Okay. So, all 100 planes and all 110 planes are equivalent, which means there will be an equal number of sodium and chloride ions symmetrically arranged in the lattice. Now, what about the 111 plane? The 111 planes are not equivalent. Why? Because it shows an alternate rise and fall with increase in the order of n. It is not showing a gradual decrease or gradual increase in the intensity, but it shows alternate rise and fall. So, that implies the 111 planes are not equivalent. Exactly midway between two similar 111 planes, there must be a dissimilar 111 plane. The intensity of reflection is proportional to the mass of the scattering particle. So, the alternating rise and fall suggests that there will be 111 planes containing only sodium ions, only Na plus ions, and there will also be 111 planes containing only Cl minus ions, and these two planes alternate in the crystal. Okay. So, we have seen that with increase in the order of n, there is an alternate rise and fall. So, this alternate rise and fall in the intensity suggests that there will be 111 planes containing only Na plus ions and 111 planes containing only Cl minus ions, that is alternating in the crystal. So, thus we can conclude that NaCl consists of two interpenetrating FCC lattices, one of Na plus and the other of Cl minus ions. So, two interpenetrating FCC lattices, one lattice consisting only of the Na plus ions and the other lattice consisting only of the Cl minus ions, and that FCC lattice is shown in the figure here. We have the pink balls represented as Na plus, smaller Na plus, and the green balls represented as the bigger Cl minus ions. So, this is the FCC lattice of sodium chloride. Thus, from the X-ray diffraction data, you can identify to which cubic lattice that a particular crystal belong to and also the nature of that particular cubic lattice. So, today we have discussed about the Bragg's X-ray spectrometer method, which is also known as the rotating crystal method or single crystal method, which uses Bragg's law to study the crystal structure. And what is Bragg's law? It is n lambda equals 2d sin theta. We have also seen the experimental setup, which consists of an X-ray source, a single crystal. We have a detector on a rotating arm. The X-rays are generated from the X-ray tube. Usually, it is a molybdenum K alpha or copper K alpha radiation passed through a slit and allowed to fall on a particular plane of a crystal at an angle theta. The crystal is mounted on a rotating disc or rotating table, and the diffracted X-rays are allowed to fall onto a detector, usually an ionization chamber or a photographic plate, and the detector can also be rotated. So, the crystal is rotated in order to vary the angle of incidence, that is at varying angles of theta, and those planes which satisfies the Bragg's law or Bragg's condition, that is the condition for maximum intensity. So, such peaks are detected by the detector. The applications of the rotating crystal method includes identifying the lattice to which the crystal belong to, determining the lattice constants, identifying the crystal structures and also material identification. However, the rotating crystal method is limited by the requirement to grow nearly perfect crystals that are suitable for diffraction. Now, let us discuss a few questions based on today's topic. Bragg's law is used in which process? You have 4 options: X-ray production, gamma ray production, X-ray crystallography, X-ray scan. When a crystal is rotated in the rotating crystal method, diffraction spots are observed on the photographic film because you have 4 options. The wavelength of X-rays keeps changing, the interplanar spacing d changes with rotation, different lattice planes satisfy Bragg's condition at different angles, and the intensity of incident X-rays varies. The scattering of waves in Bragg's law experiment is due to option A, Einstein scattering, B, Rayleigh scattering, C, Newton scattering, and D, inelastic scattering. Next question: which of the following quantities can be directly determined from the rotating crystal method experiment? Wavelength of incident X-rays, planar spacing d of the crystal lattice, refractive index of the crystal, velocity of X-rays. Why is the rotating crystal method particularly useful in crystallography? Option A, it allows continuous variation of wavelength of X-rays. It provides direct measurement of the atomic radius. It permits study of reflections from many planes by rotating the crystal. And option D, it requires no knowledge of Bragg's law. We will discuss the answers in the next class. Thank you.